this paper on using AI to think up new inorganic materials. They submitted it in 2024, and it just came out last year. So it's been out there for a year about. I used some other sources to prepare for this, so it's very fun. The senior author, Yanji, gave a seminar, and so you get the sense what this person cared for, which was a lot of the nitty-gritty. How did we deal with the symmetry of the atoms and the distances and so on? There's lots of this in the paper. And there's also an earlier version of the paper which explains this gap of 1 year between submitting it and then getting it accepted. And you can guess what it is. Anyway, here's my topics that I'm planning on. What are inorganic materials good for? We have 2 rock enthusiasts in the audience, so I have to make sure they give credit where credit is due. How is this program called MatterGen trained? How good is it finding new materials that actually exist? Then, if we don't just want a material, but we want to have a material with certain properties, like magnetic, semiconductor, how does it do that? The last bit is the only experimental part. This is real. Can you actually make these after dreaming them up? And then I'll talk a little bit about whether that's useful to have something like that. Okay, slide. You can turn to the next slide. Working very hard at the moment. Next, how about that? Okay, here is a rock. So I didn't want to go through all of this, but I just wanted to ask you as an audience, is there any one of these topics that you find interested in I should say a little bit more about? And this is a first come, first serve kind of situation. So if you shout out something, I can tell you a little bit how inorganic materials interface with these topics. Yep. Solar panels. Okay. So solar panels are inorganic materials that when you shine light on them, electrons get excited. And if you build it perfectly, then these electrons won't fall down into the same spot, but they will actually get transmitted. And you can use that to capture the free energy from sunlight and get it into electrical power. So it's very cool. There's some simple materials like amorphous silicon you can use, but you can't bend them. So I'm still waiting for the perfect solar panel that I can roll out on the top of my car to shade it and plug it in at the same time. So that would cool down my car in the summer, but also charge it. I'm also waiting for the solar paint. Our house is not very stable, and it will fall down if we try to put solar panels on top of it. But if we could just paint it and attach 2 leads to it, that would be cool. Or have a solar panel that's translucent that you can put on the windows. But there's all kinds of ideas what you could do. Should I answer one more? What would it? Yeah.
Building materials.
Building materials. So classic building materials are brick. Those are inorganic materials. You have glass, which is not a crystal. We're talking about crystals here. It's an amorphous material. Cement. Concrete, which is a mixture of cement and rocks. You get good stability, and then they also put iron rods in there, so you get tension. So you can build all kinds of cool things by having these structural materials. Okay, so this is the first figure from the paper. Except for the first and last slide, I was boring. I just took the figures that are in the paper, but I think you guys should learn how to use these figures, so I did that. There's a lot of stuff in there, so I'm going to zoom in. This is the basic idea, that you build a neural network where you can throw in atoms in a big jumble, and then it moves them a little bit. And every now and then, says, oops, oh, I'm going to turn this into like a manganese or turn this into aluminum. So you can see that the colors are changing. The other thing it does is it builds the crystal lattice. So you're starting with a jumble, and then you say, oh, this will repeat every step like this. So here I brought a crystal so you can see it. If you just look at this diamond, you might not see the repeating unit, but they actually put that in here. And so anything you see here is repeated over here. This is the repetition length in this direction. So I can take this and I see that it repeats every time. And I can go in this direction as well. So it's a repetitive structure. And as you're going from random to crystal, you also make the decision how big that repeating cell is and what kind of angles it has, and if it has internal symmetry. But how do you do this? How do you train something to do this? Turns out AI image generators take the same kind of idea. You say, well, I want to have a picture of, let's go with the beach because we mentioned that with the sandcastle. You start out with some random things, and then it starts moving pixels and changing colors until you have a low resolution side pencil, and then you have a high resolution side pencil. So they work the same way, and here's the trick how you could train them. And this is the key here. You couldn't do this without having a database of stable materials. So it turns out there's a database where you have 100,000 different inorganic materials, where they say this is the repeating unit, this is where the atoms are. And so you could just look at them one by one and say, oh, interesting, magnesium seems to have like a distance of 1.5 angstrom or something like that. But here, the strategy is different. You take these stable materials and then you corrupt them by moving the particles a little bit, by saying, oh, this magnesium is not a lithium, by changing that lattice, and then you get random. So now you have the training material, how to get from structure to random, but you can play that movie backwards, and you say, this is my training step. If I'm here and I go in this direction, I have something that looks closer than a real structure. I'm random, I go in this direction, it looks like a bad structure, but a little bit better than random. And so you use all these steps to train your AI. And then if you throw in something random, and the training was successful, you get a structure out that has realistic kind of neighbors and distances and repetitions, and should have a low energy. If you had told me 10 years ago that that works, I would say, well, that's strange. But I would have also not believed that you could just push a button and say, invent something that looks like a human face that's sticking that tongue out or something like that. But apparently, we've accomplished that. So, does it work? In general, if you want to know if something works, you really have to have criteria. And here they have 3 criteria that you can just read as sun, as a harmonic device. So they want the material to be stable. It doesn't help if you dream up something where atoms are stuck on top of each other, that won't be stable. You can make that material. So they have 2 criteria. The first is they run something called an energy minimization on that. So they try to see if they can move the particles a little bit so that you get a low energy. Like if there's a bond that's a little bit too long, then you would move that in a little bit. They do that and they find that most of the structures are already basically at the minimum, or just like a 10th or a 20th of a bond length away. So that means that the things that this spits out, without explicitly knowing what the right bond length is, it's sort of just implicit in the neural network. They're pretty good already. And then they do this other thing, and I mentioned this a week ago with the convex hull thing. But just to give you the brief idea again, you can make something where the elements are more stable than the thing you made because it will fall apart into elements. Or you have another compound that has a structure that has low energy. But this one has a higher energy, or it can fall apart into 2 structures that have a lower energy, then we'll do that when you heat it up. So this shows whether it's thermodynamic and more stable. Some of them are as stable as the known compounds. Some of them are maybe 0.1 or 0.2 electron volts per atom higher in energy, and that's called metastable. It's probably gonna be able to sit there for a while. Just like that diamond. Did anybody know that diamond is not the thermodynamically most stable form of carbon?
I didn't know that either.
Yeah, graphite is.
Graphite.
So diamond is formed under conditions that are not ambient, and then it's frozen in that configuration. It's not forever, but it's pretty lasting because you don't change to high pressure or high temperature, so that it can sort of relax into graphite. So that's the stable part. Then we have the unique. This is just a question. If I have a game of cards and I hand out hands of 10 cards, will I always get the same, right? Then my generation is worth less because I always get the same stuff. If I have a graphic designer and I ask them to do stuff for me, and they always give me the same results because they're just in love with that type of design, then I'm getting less value of it. So they tested this when they make 100,000 molecules, 100,000 structures, then 99% is unique. So that means that you have a big variety of different materials. And then if you go to the 10 millionths, it drops off a little bit. Then 50% you already see. You can do some statistics and say, well, then probably the whole body of unique structures you could get if you just try again and again would be on the order of 100 million, which is a lot, given that we're starting out with 100,000 or 500,000 kind of training. And the other one is that whether it's new. So every now and then this will actually, in about 20% of cases, it gives you a structure that has already been described. And that's not so unusual because you trained it with that. Right? You taught it how to make those structures from scratch. So sometimes it will make those structures from scratch, but sometimes it also will make this. Anyway, they have succeeded in making an algorithm that makes stable, unique, and new substances. And there's more to this figure. They're comparing it with previous models. So there's a whole set of models that have been trained on the same set of structures called MP. I think the Materials Project has a database with all the structures. That's what they used. And you can see that those didn't give new structures. They always gave the same thing. And if they use their new method, 20% of the structures are fun, meaning that they are stable, unique. So it's much better. But then they're also making the argument if we have a better data set. So this one is not only the Materials Project, but also the Alexandra network, which is a different database. They put it together. So they start, instead of starting with 600,000 structures, they start with 800,000 structures. They have a more bigger diversity in that data set, and so they're generating more unique substances. So they're claiming their progress in making lots of different structures is A, by having a better algorithm, and B, by having better starting material, better set of example structures. Okay, so this step sort of shows that you can push it a little bit further, but it's not new. It's just expanding the capabilities a bit. Oh, I didn't talk about this one. So this one shows how far you have to move the atoms to get into the best configuration when you minimize the structure. Here, they had to move it like by whole bond lengths. This one is like 1/10 of a bond length, and this is so little, it's like a 40th of a bond length. So what comes out, you can fairly, almost already say, yeah, that is the best structure for this set of atoms. Okay, here comes the new stuff that they're excited about. You can now say, well, I want a new structure, but I also want this to be a magnet, or I want it to have a band gap. So somebody was asking about the solar panels. The solar panels have a band gap. That's where the electrons get elevated into higher energy when the sunlight hits them. And so we need that band gap. And so this expanded model, you can say, I want a new substance with a band gap of 3 electron volts. And then not all of them actually do that, but sort of the majority is in that range. Here they're trying to make materials that are strong, that are not compressible. And here they're trying to make materials that are magnetic. So how do they do this? How is this different? How did they get it? So what they're not doing is just getting a million substances and then testing them computationally, but they're actually nudging the model to have a preference for something. And you've probably seen this with AI. You can say, well, I want you to be cool. And then it speaks like a teenager. Or I want you to be kind of short in your answers and precise. So you can change that. And this is a similar thing. You give it your preferences up front, and then it spews out different kind of answer. So this is the first slide again. So remember, we took known materials, we corrupted them, and then we used these steps to train it, so it would make a stable material again. Now we're adding something, which is called fine-tuning, and that's exactly what you would do with the model if you want to make it go in one or the other direction. I'll keep the door open. And I don't know enough to go into any kind of detail, but remember we had 600,000 structures. Then they take maybe just 5,000 structures where they know whether they're squishy or hard. And they say, this is an example of a squishy one, this is an example of a hard one. I prefer the ones that have stability. And you change that model a little bit so that it's a new model that now prefers hard rocks instead of soft rocks, or magnetic things instead of non-magnetic things. They have multiple of these models. One of them prefers certain elements. One of them prefers certain symmetries. But the one that we're going to look at is that prefers certain properties, like magnetic, or tough, or band gap, so you can use specific conductors or photovoltaics. Okay, so just to remind you why I told you all of this, and to go through these diagrams a little bit. So this is the training data set. So there were a lot of materials that don't have any magnetic properties, and then some that have a little bit of magnetic properties, and then very few that have the high magnetic density. But then on the other hand, what they actually get out, because they say I prefer those, most of the structures they get out actually have that high magnetic density. They say I prefer that. And the AI learned from looking at some that have low and some have high, found the trends, and was able to generate those. Same for the energy gap. And it might be a little bit hard to see, but it's not that there's no examples in the data training set, but there's very few examples. And here's the hard versus soft. You can see that it's not always getting these, right? So this one generates a couple of very soft materials, even though I say, well, I prefer the hard materials, but I get many more properties. Okay. So anybody have a guess why this paper was published a year after it was submitted? What might the reviewers have said? Yeah?
There's not more advanced AI systems to analyze?
No, I mean, that would be a danger, right? If you show everything, then you can always say, well, but they're 10 times better now.
Right.
Give me something I can hold in my hands.
Yeah, okay.
It's all computational.
Right.
You're claiming that these things are magnetic. You're claiming because the calculations are pretty good, but is it real? So they tried 6 of the structures, and by trying it means they take the atoms at the right proportion. So this has some Ta, some chromium, and some oxygen in there in a certain ratio. So you mix them together, you grind them up, you heat them up, you let them cool down, and grind them up again, heat them up, let them cool down again, and then you do a crystal structure analysis, and they found that it looks like they were thinking it would look like. There's a kind of tricky thing there. Sometimes you can see that the atoms are colored in 2 colors. So I don't remember how to pronounce the potential. But anyway, it likes to go in the spots where the chromium goes, so they're sort of the same size, same preferences. So there's some what's called disorder. But basically, they got the structure. So exactly the structure, but they almost got it. Sorry, I should clean up here. There's all this messiness in here. So they predicted that this material would have a bulk modulus, that's the measure in gigapascal, of 200. Or they wanted one that has 200. Their computational step told them it has a value of 220. Then they made this stuff, which is a little bit disordered, so it's a little bit different. And the value was 180. So they did make the material that is very hard compared to everything else. There's another thing where even if you don't have any hard evidence, you still get something out of it. And that's if you have a data set of structures, you can hide 10% away from them. Okay, I'm not using that for training. I know these exist, but I'm taking it out of the training. And then I'm generating materials, and they came back. So all these circles here are known materials that were not used for training. And so they can then be sure that they exist because they've been seen before and the structure has been analyzed. I don't think all of these were experimental tested for their strength, but they used the computational method to do that again and found out that if they ask for something that should have a bulk modulus of 100 gigapascal, most of them have at least that, some of them are high. So you can see that asking for a certain property actually works. You get some of it out. There's a range there, so it's not perfect, but you're getting a lot of materials that might do what you need them to do. Okay, this is my last slide. The question is, does it matter? Can we do anything with that? They make the claim that this is more efficient than screening and also more efficient than previous computational methods. So if you screen, you would make 10,000 materials, you would measure all of them, and then if you're lucky, one of them has the properties that you have. And that's the traditional way. We just discover materials, and then we ask the question. It's like the cooking field, the Saran cooking surface. They use that first in outer space as a field of that. Oh, we could make cook stoves with that. So now there's an application for that. Future directions, they themselves said in the paper they want to fix some known problems. So for some reason it prefers the simple symmetry over the more complex ones, so losing out in a lot of structures. And then they said we want to move towards real world applicability. So they said, oh, it's not enough if this thing is strong for pressing, it also has to be strong against shear forces, and we didn't build that in. That's something that's not as easy to calculate. So we want to make our model. The last link I put in there. So if you're like Lucia and say, is this even real? Turns out that making these materials is sort of always the same step. As I said, you grab the right elements, you heat them up, you grind them, heat them up, you grind them again, so they become consistent throughout and crystallize, and then you can check whether they have the properties or not. So you could link this to one of these robotic labs, and instead of trying 5 compounds, you can try 500 because it's just run all the time. So from a human perspective, this is kind of fascinating intellectually. On the other hand, it's like, what's my job if the experimental part and the theoretical part is taking over? So that's something we as a humanity have to struggle with the next couple of years. But you can also say there's some real problems that we have. Like if we had more functional solar panels, maybe we wouldn't burn as many fossil fuels, and then we would be able to sort of take a turn in the climate crisis. So that would be nice. There's some potential there, and there's some risk there. So I just want to close with the beginning slide. So this is what we talked about. So if you're thinking what kind of questions that I want to ask, that's sort of an overview. And I mentioned that this gap was because the reviewer will probably say, show me the money now. At least have one of these substances made so I can trust that it's not just in your head or in some machine. Thanks for your attention. Yeah. So now we can proceed to step 2, which is me turning off the camera. It took 26 minutes. This is like hard data.